You can say goodbye to your straw man. But while I got you got anything for this? Pittsburgh is at a latitude of 40.43 degrees. Using your triangulation method, that would be 3,169 nautical miles from the GP of Polaris. Miami, Florida is at a latitude of 25.75 degrees. That would be 5,598 nautical miles from the GP of Polaris. The distance between Pittsburgh and Miami, therefore, must be the difference in those two distances. That would be 2,429 nautical miles. The problem is the actual driving distance is only 1,026 nautical miles. Using your method, we're off by more than a factor of 2. This is a massive flat Earth fail. How about showing us where we're wrong?
I thought you'd never ask, Blue. Let's show you how we work it out on a flat Earth. And after you see this, and anybody who sees this and acts like we don't have a set position for Polaris or the sun for Eratosthenes or distances to the Polaris, after you've seen this and you still make that claim against flat earthers, you're no longer being honest. So let me break this down. The only thing I've changed here is A over 90. I got 90 minus A over 90 because I'm converting it for latitude, and I explain and show you for the couple people who give me problems with that B-ball and peanut shield. So let's get into it. Okay, so Blue gave us an angle of 40.43 degrees for Pittsburgh and 25.75 for Miami. I'm going to show you all the math. We're going to go through the triangulation and whatnot. The only change I have, and I have it explained and shown, either I've already shown it or I'm going to shortly in this video, I changed from A over 90 to 90 minus A over 90. That's to put it in latitude, and like I said, I demonstrate that. I have some issues. First issue is I'm so sick and tired of them making claims about a sextant. We can't use it on a flat Earth because of heights to Polaris. Okay, that is insane. Since when do we triangulate the heights to the stars? We do not. I would like to see them try to triangulate for light years away. So if we have to triangulate, so do y'all. And y'all be triangulating to stars zigadillion miles away. It's insane. It's like, and I have an equation here, and it's simply a function of distance. It's refraction with using a function of distance compared to the angle. So it's a ratio of the angle to the distance. It's simple. There's no arbitrary numbers. There's no 7 over 6R bullshit made up stuff. This is the angle we observe and the distance it triangulates to. Okay, it's all proportional. It's simple. Okay, you make your own equation, and no, you can't. You can't have your own equation. What the? We already have equations. Okay, the last equation I think for the globe was the was the ultraviolet catastrophe. There was a catastrophe. So, they just check for pre-existing equations. Can't make new equations. Oh, we already have the equation. So I'll call this the the globe catastrophe. But anyway, so I have challenges. Okay, for Blue, Marble, Science, and other globers. Okay, first off, the sextant was made for 120 degrees, 60 degrees from your star from your zenith down. So anything from 0 to 30 degrees on each horizon is you can't use a sextant. It's not going to be accurate. So I challenge anybody to show me get a triangulation from Miami from 25 degrees, from anything less than 30 degrees, and see how accurate you are. It's going to be laughable. Also, I challenge try and use a sextant. Try and get your angles of equal elevation. Try and apply them to any map at all. Even if it's a globe a projection, okay? And then you say, well, the maps are flat, that's why it doesn't work. Wrong, okay? So now that's my final and most important challenge. Try to scale your angles and your angles of equal elevation onto an actual globe and watch. You're going to be very disappointed. You could try it. You could try it with an actual globe, or you could try it on a program. It does not work. Y'all give it up. This model and the nautical miles was all formulated using a celestial sphere. Okay, so from one horizon to the other was 180 degrees. So that's the way it was equated. It does not work on a globe. I've tried it. I suggest you try it. So, this is game over pretty much. Okay, everything in this model is empirical. So we're going to start out, how do we get the height to Polaris, okay? 1 degree change over 69.1 miles. That's observable for anybody. So we put 89 degrees, 69 miles. We calculate, and what do you know? We get 3958.7, the exact globe radius. So there's how they got their radius, folks. It's what triangulates 1 degree for 69 miles. Okay, so we're going to take what Blue gave us in the challenge of the angle. We're going to put 3959, that's the calculated height. We're going to put 26 degrees for Miami. We're going to calculate, and we're going to get 8,115. So remember that number, 8,115. That is your triangulated distance from Miami. Okay, then we're going to put in the calculation for Pittsburgh. So we keep the 3958 height, and we put in 40 degrees for Pittsburgh. And then we calculate. We get 4716.9. So I put 4717. So remember that number. That's also important. Let's see what we come up with. All right, so we'll start with Pittsburgh. Say 90 minus 40 is 50. So 50 over 90 is 50 divided by 90 times 4717, which is the triangulated distance before refraction, times 0.50 equals 1310. So write that down, 1310. Now we're going to triangulate Miami, and we get 90 minus 26, 64. So 64 divided by 90 times 8115, which was the triangulated distance, times 0.64 equals 3693. So 3693. So then we are going to, that's the refracted values in distance, in miles. So we're going to subtract, we're going to say 8115 minus 3693. And we're going to get 4424. And then we're going to take and subtract Pittsburgh's refraction. So we're going to say 4717 minus 1310. And that equals 3407. So then we're going to subtract the actual distances, 4424 and 3407, for our distance between Miami and Pittsburgh on a flat earth. Okay, so Blue had 1,026, we got 1,017. Okay, this is a little quick section of the video for people asking why I subtract my angle from 90. Okay, it's because I'm putting it for latitude. Okay, so let me show you. So let's say it's 6,200 miles from the equator to the North Pole. There's 90 degrees, okay? So we say 6,200 divided by 90 times the angle. So if it's a 10 degree angle, okay, but if we're converting it to latitude, okay, we get 688. So if you're at 10 degrees latitude, do you think you're 688 miles from the North Pole? No, you're opposite. You got to put in times 80. Okay, so you say 90 minus 10, okay, equals 80. Then you do it. So 6,200 divided by 90 times 80. And that is your 5,511 miles. That's your distance from the North Pole at 10 degrees latitude. So I'm putting it for latitude on my model. So that's why I subtract it. And I'm not cheating the angle. When I'm triangulating my angle, I use the actual angle. Okay, but this is for b-ball. I mean, I thought it'd be obvious, but for a couple people it wasn't. B-ball and paid NASA shill about have a conniption fit. Why are you subtracting for that? So there's why, and there's an example. So thank you. So there you have it, folks. I don't want to hear, so how does the sun set on a flat Earth, or how can you be at multiple places for Polaris? How's angles to Polaris? I don't want to hear that no more. There's your answer. It's based on an apparent celestial dome with refracted light coming through. So if you're out at sea and you have a sextant and a map, no almanac, you could use this equation and you shall live. But just joking. One other thing, for the extreme angles getting closer towards zero, terrestrial refraction starts taking place for the extreme angles. So that model's coming out next to complete. Thank you.